will be speaking on methods of investigation of macromolecules. Macromolecules of a chemical structures are characterized by a definite molecule weight or by a molecular weight distribution, and when being in the form of coil or globules, also by their size and shape. The most important molecular weight determination methods employed in the physics of polymers are osmometry, viscometry, and sedimentation in the ultracentrifuges. The last method is especially widely used for the study of biopolymers. Osmometry is based on the measurement of the osmotic pressure of a polymer solution. According to the van der Hoef law, osmotic pressure by C is equals to RT by M, where C is the solution concentration in gram per centimeter cube, M is the molecular weight. This equation is for ideal solution, and for non-ideal solution, osmotic is equals to RT by M C plus BC square plus C square, etc., where B, C are the coefficient, are the second, third, etc. Viral coefficient. The intrinsic viscosity of a polymer solution is defined as eta is equals to lim eta minus eta naught divided by eta naught concentration, where eta is the viscosity of the solution, eta naught is the viscosity of the pure solvent. The sedimentation method consists of sedimentation of macromolecules under the action of centrifugal force in the ultracentrifuge, whose rotor revolves at a speed up to 10 to the power 4 to 10 to the power 5 rpm. The centrifugal acceleration is much greater than the force of gravity G in the modern ultracentrifuges. It reached 350,000 grams. The cell containing a polymer solution in a cylindrical with a transparent window made up of crystal quartz in place in the rotor. If the rate of sedimentation considerably exceeds the rate of diffusion of macromolecules, sedimentation occurs. Two regions form in the cell, the pure solvent and the polymer solution. There is also a transit zone where the solution concentration C varies from zeros to certain maximum values. As the sedimentation progresses, this zone and its boundaries are displaced. The viscosity of travels of the boundaries towards the base of the cell, that is from the axis of the rotation of the rotator, is measured. A sedimentation coefficient of the value of 1 into 10 to the power minus 13 S is called as Sudberg unit. The positive as successive time of the sedimentary boundaries layers are photographed in ultraviolet light. By measuring as D, P and P naught, it is possible to determine M. The sedimentation coefficient as depend on the solution concentration due to the hydrodynamic interaction of the molecules. It increases with increasing M. For example, the value of S0 for myoglobin, hemoglobin, and phycoerythrin are respectively 2.0, 4.5, and 12 S. The corresponding value of the molecular weights are 17,600, 68,000, and 2,90,000. With low rotational velocities of the ultracentrifuge, a state is reached where the rate of sedimentation equals the rate of diffusion, and a state of equilibrium sedimentation occurs. As significantly, equilibrium distribution of the material. At sufficiently large D, the equilibrium set in rapidly and there is observed an equilibrium distribution of the material. If C is the concentration of the dissolved polymers at a distance x from the axis of rotation, then the number of molecules undergoing sedimentation during time dt unit surface perpendicular to x is equals to C dx by dt into dt, where dx by dt is the rate of sedimentation at the distance x. During the same time dt, the amount of salt that diffused through the same cross-sectional area is equals to d dc by dx dt. At equilibrium, c dx by dt is equals to d dc by dx. In the Archibald method, which requires a lower consumption of material and time, not the equilibrium itself, but the approach to equilibrium is investigated. The flow of material through the meniscus and the base of the cell have a zero value, independent of the attainment of the equilibrium. When light is scattered by macromolecules, and the next topic I'm speaking on polyelectrolytes. Many macromolecules, including proteins and nucleic acid, are macroions in aqueous solution, carrying a multitude of charge groups. Example is polymethyl acrylic acid, which is a polyanion. Bipolymers are polyamorpholites. They contain both anionic and cationic groups. Protein contain acidic and basic residues. Nucleic acid contain acidic phosphate groups and the basic nitrogenous bases. There exist solid macroions and flexible polyelectrolyte chain. Evidently, the properties of such macromolecules depend subsequently on the interaction of charges present in them. The magnitude of these charges depends on the degree of dissociations of ionic group and the ion atmosphere that surrounds them. The conformation of flexible polyelectrolyte chain is determined by the minimum condition for the sum of conformational and electrical free energies. Naturally, the presence of like charge in the chain means their mutual repulsion, which lead to the uncoiling of the chain macromolecules, whose size is thus increased. The electrostatic free energy of the coil is calculated with the account taken of the ion atmosphere. Fleury has worked out a theory of size of polyelectrolyte chain, which is similar to the theory of volume effect proposed also by him. It is assumed that the coil and the solvent immobilized by it are electrically neutral as whole. Calculations show that electrostatic interaction cannot convert the coil into an extended chain. Only the expansion of the coil occurs. This is an agreement with experimental data, with the dependence of intrinsic viscosity on the molecular weight. It is more rigorous statically theory of charged macromolecules. It is taken into account that because of shielding by counterions, the charge group of the macromolecules situated far away from one another along the chain interaction only during their accidental propose due to the fluctuation. From this theory, it follows that the conformational property of charged macromolecules are intermediate between the properties of unswollen random coil and rigid rods. The greatest extent of uncoiling of the macromolecules of a polyelectrolyte is attained at a low ionic strength. This data has been obtained by the light scattering method for solution containing no salt. The degree of dissociation of the polyacid is controlled by the addition of base. In such a case, of course, the ionic strength does not remain constant. The expansion of the coil increases with dilution of the solution, since a decrease in concentration of the polyelectrolyte at constant degree of dissociation means a decrease in ionic strength. Information of the structure and properties of polyelectrolyte macromolecules in solution can be obtained through the use of ionic dilution. The polyelectrolyte solution is diluted by a salt solution with ionic strength equal to ionic strength of most concentration polyelectrolyte solution in order to maintain the total concentration of the counterion constant. Counterions can be bound by the charge group of a polyelectrolyte in a specific way. Such binding depends on the chemical nature of the macroions and the small ions. Specific binding, which boils down to the formation of salt linkage at fixed point of the macromolecule, should be differentiated from non-specific binding, which consists of the formation of an ionic atmosphere. The counter ions in a salt linkage is at a considerable shorter distance from the charge group of the polyion than the distance between this group and the mobile. The specific binding of counter ions determines the ion exchange properties of polyelectrolyte, which find important practical application. A cross-linked insoluble polyelectrolyte which undergo swelling in water or in other liquid media are used as an ion exchange reagents or ionides. Ion exchange reagents are capable of sorbing certain ions from solution. This ability of ion exchange reagent has found application for the purification and separation of various electrolytes and for the purification of non-electrolytes from ion impurities. In polyelectrolyte and hence in biopolymers, salt bridge can be formed between the cationic and anionic in a single change or in a severe change. Investigation of the structure and properties of biopolymers must of necessity taken in account their polyamorpholite nature and hence the pH and ionic strength of the medium. The structure of native molecules of protein and nucleic acid depend to a considerable extent on the electrostatic ionic interaction.